Now this video is just a short introduction to why we differentiate. So it's aimed for people in higher level or ordinary level, and some of you might be just starting differentiation for the very first time. Some people might be just going back over it, and it should suit everybody really, and it's quite important that no matter what level of differentiation you're doing, you understand why you're actually doing it. Okay, so at this stage, we should all know how to differentiate, okay? Whether it's your basic fundamental differentiation, where you're reducing the power and multiplying by the coefficient, or if you're in higher level, then you have your rules, your product rule, quotient rule, chain rule, and then you have your kind of different functions then that you need to know the rules of differentiating as well, right? But that's not what this exercise is about. Before you go into this exercise, it's kind of essential really that you do know how to do all of those things. Okay, whereas what we're going to focus on now is why we differentiate, right? So all of these things now, they might be familiar to you. If you've done this already, these things, you might even know how to do them. But the big thing is why do we actually use differentiation to do these things? So this worksheet essentially explains these three concepts. Okay, so why is differentiation related to slope? I'm going to introduce these two key questions, which I'll explain later on. And why is differentiation related to the turning point? Okay, so you might know that rule, you might make the connection with differentiation in that rule, but why do we actually use differentiation to do all of these things? So that's what's going to be explained now in this worksheet. Now, it's kind of important that whether you're higher level or ordinary level, if you're a student, be filling this worksheet out as you go along, right? You're not really learning much by just listening to the teacher or listening to me explain this worksheet. You're better off actually doing these tasks yourself, because that's where the real learning occurs. Okay, and you can go through it either with your teacher then, or listen to this video to kind of explain the different features of it. So make sure and have the worksheet out in front of you, whether you're higher level or ordinary level, as we do this. So the first thing about differentiation is it's all to do with slope. Now in coordinate geometry, you remember well how to calculate the slope of different lines. So you can use your formula, your slope formula, or more probably what most people end up doing is using the rise over the run formula. When you have the actual graph in front of you, rise over the run is much more effective at finding the slope. But that's just a small bit of a recap there of that. And just remember as well, that's actually quite important for later on, that if you have a horizontal slope like this last one here, that is a slope of 0, right? Which will be important later on. Some of you might know why already. And then this kind of concept then as well, like the other way around, if you're given the slope and you're given a point, how do you actually draw the line, right? Well, the slope formula is rise over the run. So if the slope in this case is 2 over 3, that means it rises 2 and it runs 3, so up 2 and across 3. So your next point is going to be here, right? Then it's going to go up 2 and across 3, so the next point after that is going to be that point there, etc., etc. So from that, then we can draw that line, right? So if it's minus 1 over 5, that means it's going to go down 1 across 5, down 1 and across 5. So there's your slope, or there's your line. And if it's just 4, well, 4 as a fraction is 4 over 1. So 4 over 1, up 4, across 1, rise 4, run 1, and there's your line. Okay, so that's just a small bit of a recap there on what slope is. And this is the important thing here. All right, so here we have a function, okay, a quadratic function. It could be any type of function, but this is a quadratic function we're dealing with. And the essential investigation here is how, if we draw a tangent to that function, right? So if we pick a point like minus 4, minus 5, this is what and this is a separate point, 0, minus 1. And if we draw a tangent, so that's what a tangent is, a line that touches the point at exactly one point. It doesn't go inside the curve. That's what a tangent looks like. So there's the tangent at the point A. There's the tangent at the point B. Differentiation is all about how do we find the slope of that tangent. Throughout all of these three tasks, we're going to be answering three questions, and we want to use the graph to answer the question, and then we're going to use differentiation or calculus to answer the question as well. Okay, so again, it's important that you do this now as we go through it. Don't just sit and watch the video. Actually carry out the exercise is much more effective when you're learning. So the very first step is we're going to use the graph we're going to identify A and B on our graph, so that should be straightforward enough. There's A, there's B. Now this is the tricky part. If you're doing this physically, construct a tangent to the function, right? So it's going to be slightly awkward here. You might get it slightly incorrect. Like, it's very difficult to get this 100% correct. But all you're doing now is drawing a tangent to this point A. right? So get out your ruler and just draw a straight line that only touches the curve at the point A, okay? And it doesn't go through the curve, it just goes through the tangent. It should end up looking something like this. Okay, now what you'll find is that it's quite difficult to do that completely accurately, right? But there's your tangent, there's your tangent then at the point B. And then what you're going to do is try and estimate the slope of those two lines. Okay, so from the slope formula, rise over the run, the best way to do this is try and find two definite points on the line, right? So there's a point, there's a point, there's a point, that's obviously a point, that's obviously a point down there. Now your line might be slightly different, it might be a slightly different slope depending on how accurate you are. But if you did it 100% accurately, which is a difficult thing to do, you should spot that your slope is -3 over 1. -3 over 1, -3 over 1. So the slope in this case is going to be -3. Okay, now as I said, that's a difficult thing to do, like, because you mightn't have drawn your graph 100% accurately. So you might have got -4, you might have got -2, or you might have got a decimal or a fraction or something like this. And it's the same with this one. We're looking for a couple of definite points on this line. So if we move up the line, you can see that that's a definite point here. If we move down the line, you can see that that's a definite point here. And you can see that the slope in this case is out 1 and up 5. Out 1 and up 5. So the slope in this case is 5, a rise over run of 5. Okay, but again, constantly kind of reiterating this, that is a difficult thing to do accurately if you're just using a ruler to calculate that. So now, where does differentiation come into this? Okay, so the big thing here is that the original quadratic, this green function here, that is the function for this quadratic graph. Okay, so this is unique to this. If you wanted to go into a bit of detail on it, you can see that the shape is a U shape. You can see that the y-intercept is -1. You would have dealt with that in the functions chapter, what the connection between this quadratic and this graph is. Now the big thing now is what happens when we differentiate this, when we find the first derivative of this. So x squared goes to 2x, 5x goes to 5. Here's the derivative now of this. And I like to draw them in different colors just to show that this is a completely different function to this. There's huge connections between them, but it's a different function. Okay. Now what the first connection you need to make is that this function tells you everything about the slope of the original function. Okay, I'll repeat that there. Here's your original function, here's your derivative. Anything to do with the slope of the function is this derivative is that what we're going to be using. Okay, so in this case, let's go back to what did we do originally? We tried to use the graph to calculate the slope of the tangent, this slope of this line here. Whereas now, if we want to use calculus to find the slope, we take our derivative, 2x plus 5, and we substitute in the x value of the point A. Okay, and it's as simple as that. When we do that, we get a slope of -3, which is exactly the same. If we want to do the same with slope B, again, we take our derivative, 2x plus 5, substitute in the x value only of the point B, and again, that comes out as 5, which is the exact same answer. So the fundamental thing about calculus is exactly what we did there, right? So you might think that's quite a trivial thing, but that is one of the most important things really in mathematics, that you can get the slope of a tangent, not by measuring it, which is quite difficult as you can see, but by using a simple calculation to do that. Now, the second type of question then, this is even more difficult again, right? So how would you use your graph to find where on this graph will have a slope of -1? Right? That's a bit more challenging now, using the graph to do this, or trying to do this manually. Okay, now the way I would do it is I would draw a line with the slope of -1 randomly, right, over here somewhere, right? So a slope of -1 means it's going to be down 1, across 1, down 1, across 1, down 1, across 1. So I would just draw a random line like that, right? You can see there, down 1, across 1, down 1, across 1. And now draw a line parallel to that, all right? So use your set squares, or use a kind of a construction, a geometry construction, to draw a line parallel to this, and find where does it touch this curve then. Right, so what you'll find is that the only parallel line to this that just touches it here at this point. Again, difficult thing to do manually, but if you did it, you'll find that the function, the point that it touches the function is -3, -7. Now that, as we know, is a difficult thing to do. it's a difficult thing to do manually, and it's quite a lot of effort as well. Like if you didn't have this function, you'd have to draw the function, you'd have to draw the line, you'd have to use parallel lines to get that, and even after doing all of that, you mightn't get the right answer, okay? But then, what if we wanted a much more accurate, a much more efficient way of answering the exact same question? Well, like the last time, we're going to use calculus or differentiation now to do that. Okay, and this is where now I'm going to introduce the next kind of concept, which is my two key questions. Okay, now the first of these key questions is which function am I going to use? Okay, and the second key question is, are we going to substitute or solve, which I'll explain in a second. So we've already established that the original function is my quadratic, and my derivative is when we differentiate the original function. And again, in the previous task, we said anything to do with slope is going to be my derivative. So that's what I mean by which function. Am I using my original function or am I using my derivative? So slope is mentioned, so it must be the derivative. But in this case, it's slightly different. In the previous question, we were substituting our value into the derivative. Okay, and that's how we found our slope. Or in this case, we have the slope and we're trying to work backwards to get our value for x. So that's why in this case, we're actually solving, right? So we're putting the function equal to -1. We're putting the derivative function, equal to -1 and solving. Okay, so that's where the two key questions come in. Which function are we using? In this case, it's the derivative. Are we substituting or solving? Well, we have the slope, so we're putting it equal to -1. And the key thing is here, a lot of people just use maybe trial and error or try and guess their answer here. But as Leaving Cert students, you should be solving this equation. So taking 5 from both sides, divide both sides by 2. So our value for x is -3, which is correct. Okay, which is the same as what we got when we did it manually. Now the question is then, how do we get the -7, right? So now we go back to our two key questions. Well, to get the y value, which function do we use? Well, actually in this case, we use our original function. Okay, so we take our original function and we substitute our value for x into that original function. And I know that kind of sounds a bit confusing there if this is new to you, or if you haven't really done with this before, if you haven't understood it before. If you just boil it down to these two questions, which function do I use? Original function or derivative? Am I substituting or solving? So solving in this case, substituting in this case. But if you boil it down to those two questions, nearly everything in Leaving Cert differentiation is related to these two key questions. So if you can answer these two key questions, or if you can even ask those two key questions, that goes a long way into you solving this whatever problem you have in store. Okay. Now, finally then, task number 4. So we mentioned earlier that if a slope of 0, if you have a line with a slope of 0, then that means it's a horizontal line. Okay, we did that in coordinate geometry. So if you want a tangent to this function that's a horizontal line, well, the only point where that can occur is here. Okay, and it should be jumping out at you there now that is also the turning point of this function. Okay, so what if we wanted to use calculus or differentiation to answer the same question? Like we got an answer of -2.5, -7.3. That can be difficult if we don't have the graph, or if we want to calculate rather than measure it. So what we do is we use our differentiation again. So back to our two key questions. Which function are we using? Well, we're talking about slope. So therefore, straight away, we must be using our derivative. Are we substituting or are we solving? Well, we know that we want the value of x, where the slope is 0. So we're putting it equal to 0 and solving. So we get an answer. And when we solve this, we get an answer of -2.5. And we want the coordinates. So we take our x value, which function we substitute it into the original function, and that gets you your -7.3. Okay. So the reason that this is important is that is the way that we can use differentiation and algebra to calculate the turning point of the function. Okay, and that's why it works. That's kind of putting it all together in relation to slope, derivatives, all the previous tasks that we were doing. That's just why when we're looking for the derivative, we put the derivative, when we're looking for the turning point, we put the derivative equal to 0 and solve. That's why we do it. Okay, so all in all, that kind of explains these key takeaways that we started off with. When we have our original function and we have our derivative, anything to do with slope, we use our derivative. Any problem that you encounter in differentiation, you ask these two questions. What function am I dealing with? Am I dealing with the original function or the derivative? And am I substituting or solving into either of those two functions? If you just boil it down to those two key questions, that'll solve most things. And then anytime maximum, minimum, or turning point is mentioned, straight away you're just thinking, I'm putting the derivative equal to 0 and solving. And 99% of Leaving Cert questions, whether it's higher level or ordinary level, if you look back through the years, you will encounter something in the lines of a turning point or something to do with the slope or the slope of a tangent. And even when things get a lot more complicated, it all boils back to everything that you can see on this slide here.